Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine the absolute bottom of the Mediterranean Sea. I mean, we are talking over 3,000 meters down, right in this place called the Capo Passero site, which is just off the coast of Sicily.
Right, and it is a completely alien environment down there.
Oh, absolutely. The pressure is just immense, like hundreds of times greater than what we feel at the surface. And it is pitch black. I mean, the only light you might ever see comes from the faint bioluminescence of these weird deep-sea creatures.
It's freezing, it's quiet, and it is almost entirely undisturbed.
Yeah, exactly. And sitting right there on the floor of this abyss is a massive, silent machine. It's basically a grid of glass spheres suspended on cables, forming this structure that is the size of a cubic kilometer.
And it doesn't move. It doesn't make a single sound.
No, it just waits.
It waits in that absolute darkness for a ghost. Literally, a particle that is so elusive, so, unbothered by physical reality that it can travel across billions of light years of empty space.
Just flying through the void.
Right. It enters our solar system, passes straight through the Earth's crust, blasts right through the boiling liquid iron of the outer core, and just emerges out the other side without even slowing down.
It doesn't bounce off anything. It leaves no wake. I mean, to this particle, the solid matter of our entire planet might as well just be an empty vacuum.
Which is what makes it so incredibly fascinating.
It really is. And the reason we are, venturing into that pitch black ocean abyss today is because back in February of 2023, that silent machine didn't just catch one of these normal ghosts. It caught an absolute titan.
It really did. It recorded a singular microscopic particle carrying an amount of energy so staggering, so terrifyingly vast, that it actually threatens to rewrite our understanding of the universe's ultimate limits.
Yeah, the event was quietly cataloged as KM3230213A. Catchy name, right? But what that string of letters and numbers actually represents is a violent collision with the deepest mysteries of physics.
The sheer physics of this event is honestly difficult to overstate.
Right, because we are talking about a particle that is essentially massless, right? A speck of subatomic nothingness, just slamming into our reality with 220 petaelectron volts of energy.
Exactly. And to find the source of that kind of power, you really have to look past the normal, quiet processes of the cosmos.
You have to look at the high-energy universe, like the cataclysmic, the ancient, and the catastrophic stuff.
You do, because standard stars don't do this.
No, they don't. And for anyone listening right now, I want to stress that this isn't just some abstract accounting error in a theoretical physics paper. This is about probing the actual architecture of reality.
The literal rulebook of the universe.
Yeah, the laws of physics that govern the device you are listening on, the biology of your cells, the gravity holding you to the floor. I mean, those laws are currently incomplete. We know they are broken at the extremes.
And this single 220 petaelectron volt ghost might be the exact tool we need to find out what the real rules actually are.
So we need to break this down mechanically, because before we can even get to the underwater trap or, the crazy cosmic origins, we have to start with the anatomy of the phantom itself. We are talking about neutrinos.
Right, the neutrino. It is perhaps the most solitary particle in the entire standard model of physics.
It's kind of the ultimate loner.
That is a perfect way to put it, because to understand its isolation, you have to look at how particles actually communicate with one another. I mean, in the quantum realm, interaction is communication.
Right, like how electrons push away from other electrons because they communicate via the electromagnetic force. They exchange photons.
Exactly. And quarks bind together in the nucleus because they communicate via the strong nuclear force by exchanging gluons.
So they basically have a mechanism to say, I am here, get away from me, or I am here, stick to me.
Yes, exactly. But the neutrino is entirely blind to electromagnetism. It carries zero electrical charge.
So it literally cannot feel magnetic fields, and it cannot interact with light at all.
None. And it is also completely blind to the strong nuclear force. So it just ignores the dense cores of atoms. Out of the fundamental forces of nature, the neutrino only feels two of them.
Gravity and the weak nuclear force.
Right. And since gravity is incredibly feeble on a subatomic scale, that really just leaves the weak force.
Which, true to its name, doesn't give you a whole lot of stopping power.
No, it really doesn't. The weak force is notoriously short range. I mean, for a neutrino to actually interact with another particle via the weak force, it essentially has to score a direct head-on microscopic collision.
Like hitting a bullseye on a dartboard that's a mile away.
Smaller. It has to hit a quark inside a proton or a neutron. And because atoms are famously, 99.99999% empty space, the odds of that direct hit are astronomically low.
I remember reading once that you could fire a neutrino through a block of solid lead, a light year thick, and there's a very, very good chance it just emerges completely untouched on the other side.
It's entirely possible they are that non-interactive.
So this brings us to the characteristic that, frankly, completely breaks my intuition about this specific particle, KM3230213A. If a neutrino is just this ghostly, non-interacting point in space, how does it carry energy?
Ah, right.
Let's just look at the numbers for a second. The detection from February 2023 was calculated at 220 peta electron volts. That is 220 million billion electron volts.
It's a staggering number.
It is. And in classical physics, I mean, kinetic energy is basically mass in motion, right? A heavier object hits harder. But physicists spent decades thinking neutrinos had literally zero mass, and even today we know their mass is just infinitesimally small.
Practically zero.
Right. So if you have almost zero mass, where is that 220 million billion electron volts actually being stored? It sounds like saying a literal speck of dust hit you with the force of a freight train. How do we even wrap our heads around that?
Well, you are hitting on a fundamental disconnect between classical physics and relativity here. I mean, in high school physics, we are all taught the kinetic energy equation, right? 1/2 mass times velocity squared.
Yeah, that's the one. Where if his mass approaches zero, the energy should approach zero.
Exactly. But that equation is really just an approximation for things moving slowly. When you deal with a high-energy universe, you have to throw that out and use Einstein's full energy-momentum relation.
Right, so everyone knows E equals mc squared. But that's not the whole equation, is it?
No, it isn't. The full equation is actually E squared equals PC squared plus MC squared squared.
Okay, unpacking that a bit.
So the P in that equation stands for momentum. So a particle's total energy is actually a combination of its rest mass and its momentum.
Oh, I see. So for a heavy particle that's just sitting still, the momentum part is zero, and you just get the classic E equals mc squared.
Yes, exactly. But for a neutrino, the rest mass is so vanishingly small that the mc squared part of the equation is basically irrelevant. It drops away. Almost 100% of its energy comes entirely from its momentum.
Wow. So it's not hitting hard because it's heavy. It's hitting hard strictly because it has been accelerated to a velocity so incredibly close to the speed of light that its momentum approaches the macroscopic scale.
It is a pure, concentrated bullet of relativistic momentum. And to put that 220 PeV into perspective, let's look at the most powerful machine humanity has ever built.
The Large Hadron Collider in Switzerland.
Right. The LHC is a 27-kilometer ring of superconducting magnets cooled to near absolute zero, designed to basically smash protons together.
And when it is running at absolute maximum capacity, it pushes particles to about, 13.6 tera-electron volts, or a TeV, right?
Yes, and a single TeV is often compared to the kinetic energy of a flying mosquito.
Okay, a mosquito.
Now, taking the macroscopic energy of a flying mosquito and cramming it into a single microscopic proton is an astonishing feat of human engineering. But the universe scales this up brutally.
Because a peta-electron volt is 1,000 tera-electron volts.
Exactly. So 1 PeV is 1,000 times more energetic than a mosquito. And KM3230213A was carrying 220 of them.
So it was a single subatomic point carrying the physical kinetic force of a dropped brick.
A dropped brick, entirely contained within something smaller than an atom.
That just stretches the limits of imagination. I mean, we are not generating anything close to that on Earth. We are maxing out around 14 TeV. This thing arrived at 220,000 TeV. The machinery required to impart that kind of momentum to a particle just cannot be a quiet star.
No, it requires violence on a cosmic scale. When physicists look for the sources of PeV neutrinos, they are looking for engines of extreme gravity and magnetism.
Like what?
Well, they look at active galactic nuclei, for one. These are supermassive black holes at the centers of distant galaxies that are actively feeding on matter.
Oh, right. And as the gas and stars get shredded and pulled into the black hole, the magnetic fields get all twisted up, right?
Extremely twisted. They form these massive relativistic jets that just shoot out from the poles at near light speed.
So the magnetic fields around the black hole are essentially acting like the superconducting magnets in the LHC, but just on a scale of light years.
The acceleration mechanics are very similar, but orders of magnitude more intense. Particles get trapped in the shock waves of those jets, just bouncing back and forth across the magnetic boundaries.
Gaining energy with every bounce.
Exactly, until they are finally ejected out into the void. Or another option is we look at kilinovae.
That's the catastrophic collision of two neutron stars, right?
Yes. The sheer density and the gravitational collapse of those events create magnetic fields trillions of times stronger than Earth's. I mean, these environments are the universe's natural particle accelerators.
Okay, so that sets up the stakes perfectly. We know there are these apocalyptic engines out there in the deep universe spitting out these relativistic ghosts. And the ghost travels in a straight line for millions, maybe billions of years.
Completely untouched.
Right. It enters our solar system. It approaches Earth. And this brings us back to the Capo Passero site in the Mediterranean. Because if this particle passes right through planets, how did that grid of sensors at the bottom of the ocean actually catch it?
That is the million-dollar question.
Let's dive into the mechanics of the underwater trap and, the famous blue flash.
Well, to detect a particle that refuses to interact with anything, you obviously cannot build a traditional telescope. You can't just point a glass lens at the sky.
Right, because it would just go right through the glass.
Exactly. So you have to build a giant volume of target material and simply wait for a statistical miracle. You need a space where the ghost, against all odds, happens to hit the nucleus of an atom directly.
And the target material in this case is the entire Mediterranean Sea. But the immediate question that comes to my mind when looking at the CAM3NET project is the location.
Why put it there?
Yeah. If I want to observe high-energy cosmic phenomena, my instinct is to get as high up as possible, put a satellite in orbit, or build an observatory on a high-altitude plateau in Chile. Why go 3,500 meters down under billions of gallons of salt water to look at the sky?
It's a great question, and it's because the ocean isn't the lens of the telescope. The ocean is the shield.
A shield.
Yeah. The surface of the Earth is incredibly noisy from a particle physics perspective. I mean, we are constantly being bombarded by standard cosmic rays, protons, alpha particles, electrons.
Right, and when these hit the upper atmosphere, they create a kind of chaotic shower of secondary particles that just rain down on the surface constantly.
Exactly. So if you put a sensitive neutrino detector on a mountaintop, its sensors would be completely overwhelmed by this constant static.
It would be like trying to listen for a pin drop while standing next to a jet engine. The signal of a single rare neutrino would just be totally lost in the background radiation.
Precisely. So you have to bury the detector. And the further down you go, the more the surrounding matter filters out the noise. Kilometers of seawater provide an excellent dense barrier against all those standard cosmic rays.
But wait, the Earth itself provides the ultimate filter, doesn't it? Because the CAM3NET array is essentially looking down, not up.
Yes. It uses the entire mass of the planet Earth as a shield to block everything coming from the other side.
Because the only thing that can travel through the Earth from the opposite hemisphere and emerge into the Mediterranean seabed without being stopped is a neutrino.
Exactly. So the detector just sits in the quiet, isolated dark, waiting for a neutrino to make that 1 in a trillion interaction via the weak nuclear force.
Okay, let's mechanically unpack that interaction, because the detector doesn't actually see the neutrino itself, right? It sees the shrapnel.
Yes, the shrapnel. The interaction itself is a really sudden, violent transformation. Remember, the neutrino is carrying 220 PV of momentum. When it finally strikes a quark inside an oxygen or hydrogen nucleus in a water molecule, it initiates a weak force exchange.
Specifically, it exchanges a heavy, unstable particle called W boson with the nucleus.
Right.
This is the actual mechanism of the weak interaction. They're literally trading a particle.
They are, and the result of that trade is fundamental transformation. The neutrino ceases to be a neutrino, its energy and quantum numbers are transferred, and a new particle is created right there in its place.
And in the case of KM3230213A, the interaction produced a particle called a muon.
Exactly, a muon.
Which is essentially a much heavier, highly unstable cousin of the electron, right?
Yes. And crucially, unlike the neutrino, the muon actually carries an electrical charge. Furthermore, because of the laws of conservation of momentum, this newly born muon inherits a vast majority of that 220 PV of energy.
Oh, wow.
So you suddenly have a highly charged particle violently tearing through the water at a velocity so close to the speed of light in a vacuum that the difference is basically marginal.
And this triggers the phenomenon that KM3NET is actually looking for, Cherenkov radiation. The famous blue glow. I mean, you see this in pictures of underwater nuclear reactors, right? That eerie, vibrant blue light.
I do, yes.
But the mechanism behind that glow is wildly counterintuitive to me.
Yeah.
It happens because the muon is moving through the water faster than light itself can move through the water.
It is counterintuitive. The concept of moving faster than light often trips people up because of the hard cosmic speed limit that Einstein established.
Right, nothing can go faster than the speed of light.
Exactly. But Einstein's limit, which is roughly 300,000 kilometers per second, applies strictly to the speed of light in a perfect vacuum.
Ah. Oh, yeah.
When light enters a medium, like glass or, water, it interacts with the electromagnetic fields of the atoms in that medium, and its propagation speed drops. In water, the phase velocity of light is only about 225,000 kilometers per second.
But our 220 PeV muon doesn't care about the water's optical speed limit. It is being pushed by such immense relativistic momentum that it plows right through the water at 299,000 kilometers per second.
So it is literally outpacing the local speed of light.
It's blowing past it.
And the physics of what happens next is beautifully violent. As this highly charged muon rips through the water molecules, its electromagnetic field forcefully pushes the electrons of the water molecules out of their stable orbits.
It displaces them. It's physically shoving the localized electromagnetic field out of the way.
It shoves them aside and then immediately passes by. But once the muon is gone, those displaced electrons violently snap back into their original stable positions. And when an electron snaps back to a lower energy state, it releases a photon.
A packet of light.
Exactly.
But if the muon was moving slowly, those photons would just randomly scatter, right? It would just be a faint, disorganized glow.
Oh, it wouldn't even be a glow. If a particle moves slower than light in that medium, the polarization of the molecules is symmetrical front and back. The electromagnetic disturbances cancel each other out, resulting in absolutely no net radiation.
Oh, interesting.
But because the muon is moving faster than the emitted photons can travel away from it, the geometry changes completely. The polarization is asymmetrical. The photons being emitted as the electrons snap back are forced to pile up on top of each other, constantly overlapping.
Okay, so it is the exact same physics as a jet breaking the sound barrier, but just translated into the electromagnetic spectrum. Like, a jet moves faster than the sound waves it creates, so the waves compress into a single massive acoustic shockwave, a sonic boom.
Exactly.
So the muon moves faster than the light waves it creates, forcing them to compress into an optical shockwave.
That is a brilliant way to phrase it, and that optical shockwave takes the form of a cone of bluish light spreading out behind the particle. That is Cherenkov radiation.
Yeah.
And that blue cone is the footprint the KM3 net sensors are waiting to catch.
So let's picture the detector array again. We have these long vertical strings of spheres anchored to the seafloor. Inside each of those spheres are photomultiplier tubes.
Yes.
And these are instruments so incredibly sensitive they can literally detect a single individual photon of light hitting them in the pitch black.
They are that sensitive. So as the muon streaks through the kilometer of water, the cone of blue light washes over the sensor grid. The photomultiplier tubes trigger, recording the exact nanosecond the light hits them and the exact intensity of that light.
And from those nanosecond timestamps, you reconstruct reality. I mean, if a sensor on the left side of the grid registers a hit a tiny fraction of a second before a sensor on the right, you know the cone is moving left to right.
Exactly. By tracking the cascade of triggers across the 3D volume, the computers rebuild the precise trajectory of the muon. And by measuring the total amount of light emitted, they calculate its total energy.
Which is how the researchers were able to trace the track of KM3230202HE and calculate that horrifying 220 PV energy figure. They literally saw the optical sonic boom left by the shrapnel of a collision that was born millions or billions of years ago.
It's incredible.
It is a profound sequence of events. A massive cosmic accelerator fires an invisible ghost across the void. It ignores every physical obstacle, plummets into the Mediterranean, hits a single oxygen atom, and spawns a charged clone that rips through the water so fast it tears a literal wave of blue light into existence.
And that light is caught by a deep-sea grid of perfectly timed glass eyes.
Yeah. But recording the event is really only half the battle. Now we kind of step into the role of the detective. We have the path of the muon. We know the angle it was traveling. So how do we use that to find the monster that fired the gun?
Well, this brings us to why neutrinos are so highly prized in multi-messenger astronomy. They are considered the ultimate incorruptible cosmic messengers.
Incorruptible. I like that.
Yeah, as Rosa Coniglione, who was the deputy spokesperson at the time, pointed out, The very properties making neutrinos so impossibly difficult to catch are the exact same properties that make them invaluable.
Like their lack of charge, their tiny mass, their weak interaction.
Exactly. They carry untampered information from the most extreme, distant phenomena in the universe.
Let's contrast the neutrino with the other things we usually look at to study the sky, like photons and standard cosmic rays. Because both of those have major flaws when you try to look across billions of light years, right?
We definitely do. Let's start with standard high-energy cosmic rays, which are mostly bare protons. Now, protons have a positive electrical charge, and the space between galaxies is not entirely empty.
No, it's woven with these massive, twisting intergalactic magnetic fields.
Exactly. So when a charged proton travels through a magnetic field, it experiences a perpendicular push known as the Lorentz force.
Its trajectory basically gets bent.
It curves. And over millions of light years, passing through the magnetic fields of various galaxy clusters and nebulae, that proton's path becomes a tangled, chaotic mess.
So by the time it finally hits the Earth's atmosphere, its arrival direction has absolutely no correlation to its original source. You cannot look back down the trajectory of a cosmic ray proton and see what fired it.
You really can't.
It's like trying to figure out who threw a bouncy ball by looking at the angle it hits you after it has already ricocheted off 10 different walls. You know it was thrown hard, but the origin is completely lost.
That's a great analogy.
So what about photons? I mean, light travels in a straight line. Why don't we just use high-energy gamma rays to map the extreme universe?
Well, photons do travel straight, but they interact with matter. Space is full of interstellar dust, gas clouds, and background radiation. High-energy photons have a very high probability of hitting something, being absorbed, or scattering.
So the universe is practically opaque to the highest energy light if you look far enough out.
Yes, but the neutrino bypasses both of these physical limitations.
Because it is electrically neutral, so the Lorentz force doesn't apply. The intergalactic magnetic fields cannot bend its path at all.
Exactly. And it is immune to the weak force's short range, so it punches straight through interstellar dust clouds without being absorbed. A neutrino created in the heart of an active galactic nucleus travels in a geodetically perfect, mathematically rigid straight line to the Capo Passero site.
Okay, but here is my hang-up. If that is true, if the flight path is a perfect, unbroken line, why is its origin still a mystery? I mean, why couldn't the researchers just take the 3D trajectory reconstructed by the underwater sensors, draw a straight line backward into the sky, and point to a specific collapsing star or black hole?
It's a fair question.
They narrowed it down to 4 broad origin zones, right? Galactic, local universe, transient, and extragalactic. Why such a wide net if the particle flew perfectly straight?
The ambiguity doesn't come from the neutrino's journey through space. The ambiguity comes from the physical mechanics of the collision inside the water and the inherent limits of human engineering.
Oh, I see.
Because when you draw a line backward across billions of light years, the tiniest fraction of a degree of error at the starting point expands into a massive sweeping cone of uncertainty at the destination.
Right, because geometry is just unforgiving at cosmic scales. If you are off by a millimeter here, you're off by a galaxy cluster over there.
Precisely. And there are 2 sources of that error. First, there's the kinematic scattering angle. When the neutrino hits the quark and produces the muon via the weak force, the muon doesn't always continue on the exact, mathematically perfect trajectory of the incoming neutrino.
Because the exchange of the massive W boson imparts a tiny amount of transverse momentum.
Yes. The muon's path is ever so slightly skewed from the original neutrino vector.
So the shrapnel doesn't fly perfectly straight from the point of impact.
It is incredibly close, especially at 220 PeV, where forward momentum heavily dominates, but there is still a fractional divergence. And then the second source of error is the detector resolution itself.
Right, because KM3net is a triumph of engineering, sure, but the photomultiplier tubes are still reconstructing a light cone through moving ocean water.
Exactly. There is scattering of light, deep-sea currents, and tiny limits to the nanosecond timing resolution. When the algorithms process all that data, they calculate a trajectory with a margin of error, an angular resolution usually around 0.1 to 0.2 degrees.
And a 0.2 degree circle in the night sky might look tiny to the naked eye, but when you project it deep into the extragalactic void, that circle contains thousands, maybe millions of stars, galaxies, and potential high-energy sources.
Which is why the researchers categorized the potential sources into those 4 distinct topological zones.
Let's run through those. So was it galactic, meaning a source located within the disk of our own Milky Way, like maybe a highly magnetized pulsar?
Or was it the local universe originating from nearby galaxy groups within a few 100 million light years?
Or was it transient? A sudden temporary explosion like a gamma ray burst that went off and has since faded to dark?
Or finally, was it extragalactic? A deep space phenomenon from the distant cosmic past.
And usually, by analyzing the energy levels and cross-referencing with other optical telescopes, observing that patch of sky at that exact time, they look for coincidences.
Right.
If an active galactic nucleus in that 0.2-degree circle flared up right when the neutrino arrived, you have a prime suspect.
You do. But because KM3 230213A arrived with that unprecedented 220 PV punch, it just doesn't comfortably match the standard models for a lot of those local suspects.
The sheer magnitude of the energy just demands something more.
It does. The event sits right on the edge of what standard astrophysical sources can reasonably produce. It is so energetic that they were compelled to introduce a viable alternative hypothesis.
And this brings us to the absolute climax of this event. The possibility that honestly makes physicists stay up at night. Because if this wasn't fired by a standard cosmic accelerator, we step into the realm of the cosmogenic hypothesis.
The cosmogenic neutrino.
Yeah, this is the idea that the neutrino we caught in the Mediterranean wasn't the exhaust of a dying star at all, but the shrapnel from a collision with the echo of the Big Bang itself.
It is one of the most sought-after theoretical particles in modern astrophysics. It bridges the gap between the highest energy particles we know of and the oldest light in existence.
Okay, let's break down the mechanics of this hypothesis, because we have to look at the interactions dictated by a concept called the GZK limit, right? The Greisen-Zatsepin-Kuzmin limit.
Yes, the GZK limit. And to understand it, we need 2 components. The first component is an ultra-high energy cosmic ray, or UACR.
These are typically stray protons that have been accelerated to the absolute maximum theoretical limits of the universe. I mean, their velocity is so unimaginably close to the speed of light that their kinetic energy makes the 220 PeV neutrino look weak in comparison.
Oh, absolutely. We are talking about protons carrying electron volts, billions of tera-electron volts.
So we have this impossibly fast, impossibly energetic proton tearing through the intergalactic void. That is ingredient 1.
Ingredient 2 is the cosmic microwave background, or the CMB.
Right.
Around 380,000 years after the Big Bang, the universe had cooled enough for the first neutral atoms to form. This period, called recombination, basically allowed photons' light to finally travel freely through space without constantly scattering off a dense plasma.
And that initial burst of light has been traveling through the universe ever since.
It has. But the universe isn't static. It has been expanding for 13.8 billion years.
And as the fabric of space expands, the wavelengths of those ancient photons stretch with it. So what started as intensely hot, high-energy light has been stretched out over billions of years into long, low-energy microwave radiation.
Exactly. Today, the CMB is just a faint, cold bath of microwave photons that permeates every single cubic millimeter of the cosmos. It sits at about 2.7 degrees above absolute zero.
Okay, so space isn't an empty vacuum. It is a physical sea of ancient microwave photons. But a microwave is low energy. I mean, if I fire a proton through a microwave oven in my kitchen, the proton doesn't care, it just passes straight through.
Right.
So how does a low-energy ambient glow interact with an ultra-high-energy cosmic ray? I mean, it sounds like trying to crash a speeding car into a sunbeam.
That is a great visual. But this is where we have to shift our frame of reference. The interaction only makes sense when you apply the relativistic Doppler effect.
A Doppler effect, like with sound.
Exactly like with sound. Think of an ambulance driving past you. As it speeds toward you, the sound waves compress and the pitch goes up. As it speeds away, the waves stretch and the pitch drops.
So the relative velocity changes the frequency of the wave you perceive.
The exact same principle applies to light. If you are sitting still in space, the CMB looks like a harmless, low-energy microwave. But if you are a proton traveling head-on into that photon sea at 99.9999999% the speed of light, relativity dramatically alters the geometry of the collision.
Because from the frame of reference of the speeding photon, the wavelengths of the oncoming CMB photons are catastrophically compressed.
Yes. The Doppler shift is so extreme that the low-energy microwaves gets blue-shifted into a devastatingly high-energy gamma ray.
Wow. So the proton doesn't see a cold bath of microwaves at all. It sees a blinding, lethal wall of gamma radiation.
Exactly. And when the kinetic energy in the center of mass frame of that collision crosses a specific threshold, the photon physically shatters the proton.
It hits the proton with enough force to overcome the strong nuclear force holding his quarks together.
Specifically, the photon excites the proton into a highly unstable state called a delta baryon resonance.
Okay, delta baryon resonance.
And this delta resonance survives for an infinitesimally small fraction of a second before decaying violently. The proton essentially falls apart, creating a secondary nucleon and a particle called a pion.
And the pion is also highly unstable, right?
Very unstable. It immediately decays into a muon and a neutrino.
A cosmogenic neutrino.
Born from the ashes of a proton shattering against the cosmic microwave background.
That is just wild.
It is. And this entire process, the GZK suppression, acts as an absolute speed limit for cosmic rays. Protons above a certain energy simply cannot travel across the vastness of the universe because the CMB acts like an abrasive friction.
It slowly degrades them through these violent collisions until their energy drops below the threshold.
Exactly.
But while the proton is destroyed, the neutrino it births carries away a massive fraction of its energy. And because the neutrino has no charge, it ignores the CMB completely. It ignores the magnetic fields. It just takes the momentum of that ancient collision and flies perfectly straight, unbothered, until it reaches the Mediterranean Sea.
And this is exactly why the detection is so provocative. The theoretical energy profile calculated for cosmogenic neutrinos, the energy they should inherit from those GZK collisions, aligns staggeringly well with the 220 PeV signature we saw.
Because the energy is so high that it is difficult for standard astrophysical models to explain without introducing a lot of complicated tailored variables. The cosmogenic hypothesis, while bold, offers a mechanically clean explanation for the sheer power of the event.
It does. It fits the data beautifully.
So if this is true, if what we caught in the Capo Pesaro site is genuinely a primordial cosmogenic neutrino, how does that alter the landscape of modern physics?
Oh, it changes everything.
The researchers actually call this potential confirmation a scientific bonanza. But why? What does an invisible piece of shrapnel from a dead proton actually allow us to do?
Well, primarily, it gives us a probe that penetrates the deepest fog of the early universe.
Because cosmogenic neutrinos are continuously produced wherever ultra-high-energy cosmic rays interact with the CMB, so they represent an integrated history of the universe's most violent epochs.
Exactly. By catching enough of them and tracing their energies and trajectories, we can look far beyond the optical horizons of current telescopes. We could basically map the cosmic evolution of ultra-high energy sources.
Effectively viewing the high-energy architecture of the cosmos billions of years ago. We're reading the fossil record of the universe's most extreme gravitational engines.
We are. But the implications honestly go much deeper than astronomy. The true prize here is particle physics itself, because the energy domain we are looking at, 220 PeV, is entirely inaccessible on Earth.
Right, because of the limitations of the LHC we discussed earlier. We max out at 14 TeV.
We simply cannot build a machine large enough or generate magnetic fields powerful enough to accelerate particles to PeV energies. I mean, to do so with current technology, you would need a particle accelerator the size of the Earth's equator.
So if we want to understand how the fundamental forces of nature behave at the absolute extreme upper limits of energy, our only option is to use the universe itself as the accelerator.
And build deep sea nets to catch the results.
Right. And observing behavior at those extreme upper limits is critical because our current rulebook for reality, the standard model of particle physics, is known to be incomplete.
Very incomplete. It is a beautiful mathematically predictive framework, sure, but it has gaping holes when you push it too hard.
You mentioned physics beyond the standard model, but to the person listening right now, the standard model is just a chart on a chalkboard. Why does breaking the standard model actually matter to human progress?
Well, the standard model is really just a low-energy approximation. It exquisitely describes the electromagnetic force, the strong force, and the weak force. It classifies all the quarks and leptons, but it operates under specific, localized conditions.
And the most glaring omission is gravity.
Yes. General relativity, our theory of gravity, deals with smooth, continuous curves in space-time. The standard model deals with quantized, discrete, erratic jumps of energy. The mathematical frameworks of the two models are fiercely incompatible.
When you try to combine the math of quantum mechanics with the math of general relativity, the equations just break down completely. They spit out infinities. They stop making sense.
Furthermore, the standard model offers no explanation for dark matter or dark energy.
Which cosmological observations tell us comprise about 95% of the total mass energy content of the universe?
Right. The standard model literally only describes 5% of reality.
That puts it in perspective.
So to find the theories that unify gravity with quantum mechanics, to find theories that explain dark matter, physicists believe we need to observe physics at exponentially higher energy scales, where the distinct fundamental forces might begin to merge into a single, unified force.
And a 220 PeV neutrino might be carrying the data of that high-energy behavior. It might show signs of Lorentz invariance violation.
That is one of the most tantalizing prospects. Lorentz invariance is the foundational principle of special relativity, the idea that the laws of physics, including the speed of light in a vacuum, are identical for all observers regardless of their relative motion.
Right.
But some theories of quantum gravity suggest that at incredibly high energies, space itself is not smooth but quantized, meaning it's made of tiny, discrete, bubbling pixels of space-time at the Planck scale.
Oh, wow. So if space-time is pixelated, then high-energy particles might experience a sort of drag as they move across those pixels, slightly altering their speed or how they oscillate.
Exactly. A neutrino traveling billions of light years at 220 PV would amplify those microscopic quantum gravity effects into something macroscopic that a detector like KM3net might actually be able to measure.
So if we observe anomalies in the flavor oscillations of these ultra-high energy neutrinos, or even delays in their arrival times compared to photons, it could provide the first experimental evidence of physics beyond the standard model.
It could be the crack in the dam that leads to a unified theory of quantum gravity.
That is the ultimate stakes of the game here. It is not just about cataloging another particle. It is about finding the thread that, when pulled, unravels the incomplete physics of the 20th century and allows us to weave the actual fundamental architecture of reality.
Which perfectly explains why the KM3net project is not just resting on this single detection.
Right, the Kepo-Passero site is actively expanding. The cubic kilometer array is designed to be highly modular. By adding more strings of photomultiplier tubes, they increase the total effective volume of the detector.
And more volume means more target water molecules, which linearly increases the statistical probability of catching the next PeV interaction.
They're widening the net to catch more ghosts. And with more data points, they can reduce those angular resolution errors we talked about.
Yes. If they can catch 10 of these 220 PeV neutrinos and trace their trajectories back with sharper precision, they can definitively answer whether these are coming from feeding black holes or if they are a diffuse isotropic wash of cosmogenic particles born from the cosmic microwave background.
We are moving from a single, isolated detection to a whole new era of ultra-high-energy neutrino astronomy. Every new capture provides another massive data point for high-energy physics, slowly illuminating the dark, unseen machinery of the universe.
It is genuinely a breathtaking scientific narrative when you zoom out and look at the whole picture.
It really is.
Yeah.
I mean, just think about it. An ultra-high-energy cosmic ray accelerated to the limits of physical reality by a primordial black hole tears across the early universe. It collides head-on with a photon left over from the Big Bang, shattered by the relativistic Doppler shift.
And from that violent decay, a ghostly, massless messenger is born.
Inheriting an impossible 220 million billion electron volts of momentum. It travels in mathematical perfection for eons, ignoring magnetic fields, passing through nebulae and dust. It enters our solar system, plunges through the Mediterranean, and hits a single oxygen nucleus.
And the resulting shrapnel rips through the water faster than light, tearing a blue optical shockwave into the absolute darkness.
Or a grid of glass spheres perfectly times the flashes, transmitting the data to the surface. A single flash of blue light containing the secrets of the ancient cosmos and the potential keys to quantum gravity.
It is the pinnacle of human curiosity and engineering. I mean, we are using the entire Earth as a shield and a cubic kilometer of the deep ocean as a lens to read the echoes of the Big Bang.
Which leaves a really profound physical reality to consider as we conclude. As you sit here, processing all of this, the universe has not stopped. The high-energy engines are still firing.
Constantly.
Right now, every single second, tens of billions of neutrinos are passing straight through your body. They stream from the sun, from the atmosphere, and from the deep extragalactic void. They pass through the roof of your house, through your cells, through the floor, and out the other side of the planet, entirely unnoticed.
Without you feeling a thing.
Exactly. And if just one of those microscopic phantoms slamming into the dark depths of the sea holds the power to rewrite our fundamental understanding of reality, what other invisible, unmeasured truths are flowing right through us at this very moment, simply waiting for humanity to build the right net to catch them?